Hi guys, we would like to welcome you again for to start our last hour in this webinar. Mr. Iliou, the floor is yours. Here you go.
Okay, must make again, right?
Yeah, you need to share, yeah.
Yeah. So that's, for example, different plants I get and I check sometimes. So that's a 5 megawatt plant. There you can see, for example, interestingly, we put the transformers in the middle, left and right, and we have A and B side, and it's absolutely identical cabling. So from the left to the right, it's always the same cabling with the same DV ports and the same AC sides. There we used like a ring loop installation. So we have two AC boxes running in parallel. So the idea is to save cabling, because if you would drive them individually, it almost doubles up the square millimeter so of the cables involved. And when you make a bridge connection, like in the automobile combination, then you can actually save some cabling. Some videos unfortunately don't play, but this is, for example, a connection fault which they've done with the second grounding of the inverter. So what happened was they used a 4-core cable with a yellow-green cabling and with the typical now black, gray, and brown to the PE. But inside the cubicle of the transformer or the low voltage side, they use this cable as a neutral. So now we have the recombination of the PE and N, the same I had in the company with the industrial complex, and we had floating and straight currents all over the shop. So this wrong connection made almost 9 amps, so 9,100 milliamps running in the Netherlands, and in UK I had a system like this over the existing infrastructure back to the source, back to the transformer. So when you remove the connection and put it to the right, to the neutral, then it went down to 80 milliamps again. So we have, like I said, capacitive couplings, galvanic couplings, and the common impedance. So because of these various earth connections in the medium voltage side and on the low voltage side of the inverters, there is a strong possibility that wires get mixed up. Here, that was a system where you can see 7 o'clock in the morning, a little spike, 7:30, then 7:40. So the system tried to come online several times a day, and it created some surges. You can see here the start and stop. So it was working for 10-15 minutes, and then it stopped again. So after fine-tuning, it started much earlier at 6:30, of course with a few kilowatts, 16 kilowatt on a megawatt inverter, but it stayed. And then you can see there's no surges anymore. It's much more smooth, and it can actually dip all these problematic starts and stops of the system, and in actual case, start and stop inverters in the field. So it's always better to fine tune on site and have a look. Like I said, the fine tuning is like this. It started with 700 volts because they put the starting voltage at 700 volt. So every 10 minutes, the system started and stopped again because it hit 700 volts. Then there was a cloud, then it stopped, and then it started again because it was above 700. So Also in nighttime, it had the same, that it stopped producing 40 kilowatts. So if you have a 10 megawatt field, we're talking about 400 kilowatts still working, and they switched it off. So right now the system is running till 5-7 kilowatt, and then it switches off. So like I said, you have no surges anymore. You don't have these surge suppressing units get hit every day 10-20 times. So instead of switching on and off all the time, this is like a big load. It stays on once it comes online. Like I said, I had to pull it down to 525 volt, and then we start and stop with the 700 volt setting. Disappeared. This system, you can see it's quite crowded. So they changed a lot of inverters and brought different arrays into other inverters. So for example, inverter number 1, which you can see it's almost like a C, goes into number 4 and hits also number 2, because they're all on the same rails. So the best system was, of course, 11 and 12. That was basically the normal setup you would do. But what I did was on the other building 8, 9, and 10 on the right-hand side, I tried to minimize the different areas into 8, 9, and 10, similar to 11, 12. And then also this system picked up. So you can do a lot while you're there. And check a system performance and try to stabilize the output and put similar systems together. That's a typical weather in UK when I build systems. So the trenches digged out half an hour later, it's full of water. So you have to pump the water or be very quick when you install systems. So that's individual things you have to think. And the high leakage in the field, like I said, this was in a pumping station. So you have 690 or 0.7 amps almost. So 690 milliamps running constantly on this earthing. And once you walk through the field, you can see the blue or greening of the copper conductor. That means you have a high possibility of a leakage current because it's already infecting the cabling. And underneath the current clamp meter, there is the plastic going into the soil. So they did install it correct, but like I said, the high leakage is just way too much. If you see row-to-row shading or some similar things, that's the output. You can see 2-3 inverters or strings are lower than it could be. So the blue one is almost 70 amps, while the other ones are 10-20 amps below. So that you can impact. If you see that in total figures, the plant was running actually very good. It had 1,030 kilowatt hours per kilowatt peak, which is not too bad for a European country. But the shaded strings are minimizing the output. So we had like 10, 12, 15% underperformance. So you end up with 900 or 875 kilowatt hours per plant because the shaded strings are via the mismatch destroying the good strings. So when you encounter that, you should install shaded strings to shaded combiner boxes. So that means all the shaded strings have the same problematic issues, because when the shaded strings take over the good strings, then the inverter will change also the output. Depends how big, if it's a 500 kilowatt, 1 megawatt or 2 megawatt inverter. So, and also once we did that, then the numbers climbed from 1,030 to actually 1,100 kilowatt hours. And the 800, 850 went up to 950. So although they are shaded, but you have the same circumstances, it can control much better the mismatch. And when you control the mismatch, typically the good versus the bad performing strings are eliminating each other. So the good performing strings go better, and the mismatched strings, which are less per combiner box, will also keep that up. That was a sample of these inverters with a row shading, with different scenarios. It looks not too bad actually, but the top one, not shaded, has 3.5 in winter time, while the middle one is 2.5 and the bottom is 1.5. So if you combine that, 3 inverters make 93 to 100 amps, while the one is 45. So we have 50% losses in comparison with each individual inverter. So once you change the bottom and the top different modules into different strings, then actually it increased immediately to 105. So you win almost 12 amps just by changing the DC combiner boxes. The good thing in that system was that lots of combiner boxes were near each other. So what I did was I changed the shaded into the shaded DC combiner box and the good sun into the better strings, and then it picked up a much better combination, and then the sunny strings, which were then all sunny, like I said, went up 12 amps per string in these scenarios, and the 45 went up at least to 51, which is also another 6 amps as before, because he's not mismatching the other strings, he's just combining each individual shaded string to each other. And that's just another option. You can see the top one, that's another scenario with different wirings, so that you have 93, 51 amps and 45. So again, 6.2, that's maybe 80% of the modules, and yeah, 3.4 is just 50%. So that was, for example, a transformer with different areas of combiner boxes, and you can see although it's a single unit, the different voltages actually. So when you have a clean top section, you are roughly at 672 volt as a MPPT, and versus the other ones, which are 655, 676, and 655. So you lose like 20 volt on different strings. It's like 1-2 modules, and the current goes down. So that's these different scenarios where you have different inverters, and the best is like in the bottom section where you have a lot of red or a lot of blue strings together into one inverter. It's always better to run it like this. That's from one combiner box. You see 100 amps after the energy audit. It goes up to 7 amps instead of 6.2 in specific dates. So you have now 100, 97.5, 93, and 51. So the ratio is changing also according to the months: May, June, July, September. So you see sometimes in July it's actually picking up quite nicely. It's almost 100 amps. That's doing similar to May. June is a little bit more cloudy. So it's changing. That's, like I said, most of the inverters derating the output 250 to 255. You will never know for sure how many percentage they are, but they start getting hotter, and then they derate the DC voltage, so they go up out of the perfect MPPT range and actually decreasing the output. So again, it's got nothing to do with the cables, maybe the AC cable, but nothing to do with the DC cable. So that means that the AC cable probably measures less than it's expected, and when it has to go up 10, 15 volts, that's too much. So either you change the tap settings of the transformer or you upgrade your AC wiring. That's a typical systems, what I check, that's 2 ohm, 2.07. It's a little bit high. I normally like to have something like 0.05 to 0.1. So there's some problem with earthing. If the earthing, like I said, is 0.06, which I did in the one system later on, when I changed the neutral to the PE, you can see how the leakage current picks up. So this inverter, which had like 60 kVA, 60 kilowatt, is at 0.06, has got a leakage current of 832 milliamps, only at the PE, not at the neutral. There it was over 9 amps. Also 0.83. This one has got 1.24, 2 watts, 2 ohm, and then you can see the high leakage current goes down. So here we have only 57 milliamps. So the possibility that the inverter with a higher voltage will derate is more possible than if the resistance is lower. You can see the output difference. It's during WEAKLIGHT, 600 watt, not 1000 watt per square meter. So the one inverter is not done correctly with the PE. It's almost 7 kilowatt, while the other one is 7.6. So it might look like this is not a big problem, but when it picks up, you can see here that it's in total it makes 65,850. So let's say 66,000 kilowatt hours versus 71,500. So this is the losses you have if the earth is not connected in these scenarios. So you're losing in a small percentage, 600 watt, 700 watt, 800 watt. But if you have a high peak performance, then you lose much more. And that's accumulating. And you can see at this sample, you lost almost 6,000 kilowatt hours. Also the heat map of inverters, which are used in UK, Netherlands, also in Pakistan, in some systems, if it's available, is quite nice because you can see the shaded, the leakage currents. So some of the inverter don't start up and produce less all of a sudden, or infiltrating other inverters, or the sun goes up or down. So you can have the different shades. Once it's harmonized, like I said, you put string diodes in again, you add you change the PE with a neutral, you add a neutral, you add a second earthing, all of a sudden the system is harmonized. It is still producing a little bit less, but it's not infiltrating and mismatching with existing other structures. So one inverter helps actually the other inverter. So the output is less dramatic and it just looks nicer and it's softer, and you can see immediately the response. That's from SMA with a quantum ISOFault. You can see quite nicely with the cluster controller the different status of insulation resistant faults, and sometimes even data logging issues. So it's not a problem of the product most of the time. It is a product. It's a problem with the installation. Here again, it's the same problem, but it shows power frequency is too low or too high. So because it cannot derate quick enough, or cannot make the fault, or cannot override the fault quick enough, it switches off, and then it troubles the frequency. Because if you lose, like in the one example, 300 kilowatts, 10 inverters or 5 inverters, it creates some troubles inside the same network. That's on a transformer side, so you can see the output and the end of the feeder with connected PV plants. So that's you can have a look once you have the systems. So when you change with a tab the existing structure, it's aligning much more nicer. So you can see you don't have these problematic issues, and it's like feeding almost in parallel. That's samples of different scenarios. You can see the 3 different phases and how much power they can actually inject. Here, almost 80 amps, and the voltage is 380. So it could be that it is a soft voltage, so that means it actually dips down. So it means it goes towards 360 sometimes. Then you change the transformer to 400 volt and you check again. Some people ask that now in the question sector, why to change it and what. The changing it's an issue to stabilize the street voltage, or to stabilize the voltage inside the industrial complex or inside a house or a school. So sometimes 380 volt is much stiffer, so the appliances work much better, less disturbances, so they can inject very easily power into the existing network structure. In some instances, they cannot change it towards 400 volts, put it on one step up, and check again if the stabilizing factor is now better, if we can inject more power, or if there's other issues arising. Normally, if it's a tight structure and in a 100-meter distance, it can easily be done. Here is a system I checked. There was no earthing done, second chassis grounding. So I do that as a measurement line, and then I put leads between each individual inverter, and then I just check when the modules or the inverters are aligned to each other, have the same earthing, what's the leakage of each individual inverter. Could be that you clean the modules right now, the leakage will go up, but it will be much better next to each other if it's below 1 ohm. So that's some cooling airflows. If you have sometimes problems with the inverters, and sometimes you don't know where the cooling flow is. Sometimes it's from the bottom to the top, sometimes it's from right to left. In this case, I had inverters in a tight room where they were actually heating up each other. So the first inverter had 50 degrees and the next inverter already had 55. So it was one column, and the last inverter was on 80 degrees inside the cabinet. So it's an increase of 25 kilowatt because preheated air is exchanged from one inverter to the other. What you can do as a remedy is you can put like a frame in between. So inside the inverters, you actually put like a panel, and then it will. You can also make it in 45 degrees. So the hot air is rising, and the bottom air gets colder air into the inverter in, and blow out to the outside. There you can see the panel. So like I said, it can either be vertical like this, or you angle it to the top left of the one inverter and to the bottom left of the other inverter. So you have an angle of 30 or 45 degrees. And then it will suck the cold air from the bottom. And because of the angle, the hot air will rise to the top. That's the topology of the old times with a transformer of Transformerless and Transformer-based inverter. So you can see the efficiency. So the higher the voltage in the Transformer-based, the lower the efficiency. So we went from 95 to 93 when you went from 150 volts towards 500-600 volts. And with Transformerless inverters, the higher the MPPT, the better the efficiency. So when you are above 500-600 volts, we're talking about 96 to 98%. If you are, as said, too hot in summertime, and you only reach 500 or 450 or even 400 volt, yes, the inverter can do that. He's got a big window right now, but the efficiency is going down. So that's the problem in summertime with some modules. They suffer if you, in combination with the inverter. And that's how you can control it. Like I said, with a banning or with the steward, you can check what do the modules actually want. 400, 500, 600 volt DC. You can do it. Okay, and once you energize the inverter, what is the DC voltage doing? Is it going down or up? That means it's not optimum towards the module. He will just change into his optimal, and then you have a derating included. So the derating is always based on the voltage you give him. So like I said, if you lose 100 volt and the margin is 16 or 18 modules only, so add 2 more modules, so you go towards 18 or 20 modules. That means 20 modules, you almost hit 1000 volt. The possibility that you are at 600-700 volt, even in summertime, is much bigger. And especially in hot environments, like in the desert, you should go with a higher voltage. That's old from my time with 50 watt modules, but you can still use that. It shows you how much from 1600 volt what energized you actually get after combiner boxes, after main DC cabling, after 100 meters of installed, after using 2.5, 4, 6 millimeter. Mostly now, most of the inverter companies give you a program, or you use a program, but it's quite handy to have that and also use the efficiency and derating factors. If that matches up what you see on site, then you know the system is actually performing according what it can do, because it has all these losses involved. That's the east-west systems I did, 2-to-1 and 3-to-1 strings. So you actually mix on purpose east strings with west strings to overcome this warning due problem in winter time. In Germany, for example, you can see it's melting already, the top section, because the top is combined with the other one, so it has the same voltage string, and during the backfeeding it will actually melt a little bit of the west-facing modules. This is also quite interesting. Again, high voltage loss. You see here, it's an old inverter, of course. It's 2011. So during high time in Germany, when they installed a lot of system, you see here 246 to 247 volts. So now one people was asking, what's the effect? You can see here the effect quite interestingly. You make 17.7 kilowatt at 246 with 550 volt MPPT. If you put the voltage down at the transformer level, now you have 237, same inverter, same system, same time. It cost me like 5 minutes. Now we go to 580. That means it's a much better MPPT value. I measured actually with a Benning 600 volt. So you can see 20 volt, still not happy, the modules, but it's already increased almost 3000 watts. Do that with 10 inverters, you get 30 kilowatt for free. So the derating starts with the AC voltage and shows mismatch on the DC side because it's transformerless, which means if the DC side is not optimized, how will it affect? It has to use some energy to overcome the long distance. And like I said, you can add cabling, so you can do like I did in Italy, because I could not change the tap setting. It was already on a different part on another plant. So I just added cable, so the impedance of the system goes down. And when you measure between neutral and phase, then it's actually the resistance counts how much increase of the voltage. So instead of having a higher voltage, 245 to 250, you are lower, and the inverter likes a lower AC because then he can increase with the load. So again, it's without the inverter, it's 230 volts. With the inverter, it's now 235, 237, and you have 20.4 kilowatts. And before it was 17.7. So almost 3000 watts for free, like I said. That's a charter what you can use if you have existing lightning strike protection, aluminum, steel. So it's just to show you the old time where you had unearthed racks in Germany, and then when you change to transformerless inverters, the earth racks, so you don't get a shock. Here they use the aluminum wire or a copper wire, and then they go straight up and combine these rails, which is enough in Germany. Like I said, in France and in UK at that time, you were not allowed to do that. You had to, and also in America, you had to single-handedly earth each module individually. That's the TNC system again. Just to show you the clamp meters where I actually check the system. So just replace the geyser or the hand wash boiler against an inverter, and you have the same output. So once you connect a TNC system, you don't have a separate earthing, and that means every pipe, every wire which is connected to the earth, heating in Germany. At that time, everything was metallic pipes. You have these individual leakage currents. So, and when you have these systems, it travels everywhere. It can go down a stairway ladder from the roof. You can measure sometimes 500 milliamps or more. Instead of wiring down with a PE. So when you now use a 5-core cable, it changed completely the picture. All of a sudden you have 0. So there is, when you have the 3 phases and the neutral, you will measure nothing. So if you have the PE connected to the inverter, you only have the high frequency noise. Nothing about phases, unbalanced loads, armored cabling, everything is more or less on 0. So if there is a problem at the inverter, he will start almost at 0 amps. So that's why a second earthing is so efficient in these circumstances, because you have a system which is not polluted with already straight currents coming from everywhere. That's these different MPPT points. It's just that you have these heavy losses involved because it shows the wrong points. That's one of my systems I did back then. You can see the east-west system is the yellow one. It's outperforming the south-facing system, 20 degree, 15 degree, almost similar. It's a 100 kilowatt system. So we're talking about 1030 kilowatt hours per kilowatt peak against 980. It's both not too bad, but like I said, the east-west facing system has got a potential, if it's correctly designed, that it outperforms a south-facing system. Sometimes it depends if the angle is steeper, that it's change the output, but overall you can make an east-west face system similar or even better. That's another sample where you can see in a 10 degree flat mounting, its ice is compared to 60, 70, 80 degrees. It is much cooler because it never faces the sun. So between April towards September, October, you can see the high output of this system, because in summertime it's expected to be less in the old data logging equipment from the solar log, but it was outperforming because it's colder and has a higher voltage than expected. And of course, in January, February, where the angle is steeper in Germany, it loses again out a little bit. But overall, it's like 4 or 5% more efficient. In the old times, a system got financed at 800 kilowatt hour per kilowatt peak in Germany. So you can see this guy is almost 1,050, 1,100. That's WEAKLIGHT performance again. East-West can overcome WEAKLIGHT performance. This one is on 70% and the other one is on 20% because it can only produce full power between 10 and 3 o'clock. You can see the output, while the yellow system East-West can outperform the system at nighttime and of course during daytime and in the morning hours. So it's not a lot of money if you think about in winter time, but it's nice to see that, like I said, especially during self-consumption, east-west is always better than a south-facing, because south-facing is a pyramid shape and it's based on summertime. And if you have a bad summertime, the system cannot recover all these losses. You can see an ETA per day of almost 98% with all inverters involved. So none of them are somehow behind, because that was always the thing. That's the typical IV curves. If you have, if you measure, that's in the old days with 15 modules and different maximas, which global or local inverter will try to see. Danfoss, for example, had a sweep configuration. So every half an hour or 1 hour, you could set that point. It actually went through the whole spectrum. Normally, it stays like within 5%. So when one module is 12% shaded, you could lose a small kink. When it's 20% shaded, it's more and more and more. So when you use now this as a string-based module, you lose 100, 200 watts very easily. And only one module of these 15 modules, like I said, was shaded at that time. The worst, of course, is when you have row-to-row shading, soiled, and different time frames of shade, and then all of a sudden you have 3, 4 different scenarios, and the inverter must decide which one he's going to use. And it does not mean that the inverter will use the absolute maximum. It could be the right side, or it could be even worse, the left side. So when he goes for the current sorting, then he pulls all strings down to maybe, like we saw in the picture, 3-4 amps, and is not going for the 6, 7, or even 10 amps. So that means due to the mismatch possibilities, you lose a lot of power. That's just to say what's the difference between 60 and 72 cells. At that time, if you have a 1000 volt DC inverter, we're talking about almost 20 modules. So 1440 cells should have been equal. So that's 0.69 volt per wafer at that time. Now they are above. So that shows you when one of these wafers is shaded, what's the possibility of outcome. And then I did these tests on the balcony in our office. So those small shades is already enough for 17% mismatch losses. And we had that also in the field. So I just want to show if that's possible to simulate, and it is possible. So depending on the diodes where they are connected, small tiny little shades, like you saw also in Italy with the reeling installed, what's happening. So these are the systems, like I said, thermal concentrated, these thermal strings connected in a horizontal or in a vertical string. It could vary from the shading, if you do it like this, between 9,720 and 10,800. So to do a fine tuning and to find strings which are not performing well, or change maybe even the string layout, it's worth it. We're talking about 1 kilowatt for free. So that's almost 1,000 watt missing during a long time. If it's cloud-based, or of course if it's based on some roof, or this is small tiny little shades. So there is like a combination of 4 or 5 strings, whatever you want to see, and that's the temperature zone on the left side. If you go for multi-string inverters, if you go for a higher inverter and it's a central grid inverter, it will go towards 3 amps most probably. And if you have 3 amps, all the other strings have got the same. So that means instead of losing almost 1,000 watt again, on the left-hand side, you have 3,240. On the right-hand side, you are at 2,160. So you lose again 1.2 kilowatt on modules built up at your house for no use at these snake configurations, because they are hotter, and then one of the modules or several modules are shaded, it will create a problem. Again, you can see here in a big installation without walkways in between, that's the temperatures. We're talking about 47 to 75 degrees temperature. So that's almost 30 degrees difference from the bottom to the top. In desert areas, it's even worse. Can also be reversed, which is quite funny. If the wind picks up a little bit, or if there's a breeze, then sometimes on top, the modules are cooler than on the bottom. So maybe the bottom is next to the soil, or there's not a big difference on the soil towards modules. That's all design issues. So if wind picks up, you have a cross wind. That means the modules on top are cooler than the modules on the bottom. If there is no breeze at all, no wind, we have again the natural cooling, or the natural heat up. That means on the bottom it's cooler than on the top. So that's also something which you can see in thermal graphics. And then you can also see why is the inverter underperforming, because the modules with 75 degrees, they are just not capable of producing more energy. So they're stuck at 560, while the inverter maybe wants 580 or 610. So he will derate on its own. So you have a variation again from 640 to 560 volt DC. That's just with the newer modules, 40 volt, also from 640 to 580. So also, if you have a inverter housing with a ambient temperature during specific time intervals, this is the typical temperature you encounter. Once you encounter that, again, the inverter's derating. As an example, sunny central, 720 at 25 degrees, 40 up to 62 degrees. At 62 degrees, it's completely off. Are we going towards question? Salem?
Yes, I think we passed the time. It's already 9:05. So
okay.
if you think to start at least 30 minutes for the questions,
Yep.
and then we finish the webinar. Let's